right, good afternoon and welcome again to the Communication Signal Processing Seminar. So I'm delighted to have Johan Ugander from Stanford be our speaker today. So Johan is an assistant professor in the Department of Management Science and Engineering within the School of Engineering. His research develops algorithmic and statistical frameworks for analyzing social networks, social systems, and other large-scale social data. He does a good mixture of theory and experimental stuff as well. So prior to joining Stanford faculty, he was a postdoctoral researcher at Microsoft Research Redmond from 2014 to 2015. He held an affiliation with the Facebook data science team from 2010 to 2014. He obtained his PhD in applied mathematics from Cornell in 2014. His awards include the Young Investigator Award from the Army Research Office, 3 best papers, so 2012 ACM Web Science Best Paper Award, 2013 ACM Wisdom Best Student Paper Award, and 2020 AAAI ICWSM Best Paper. He's also received the 2016 Eugene L. Grant Undergraduate Teaching Award from his department. Furthermore, in our conversations, I realized he spent some time in Cambridge around the time I was in Ireland. And there are people I know, which there's contacts through other sources where he's looked at TCP literature as well. Anyway, so I should, before I give the floor to Johan, I need to just mention that the seminar is, I should thank the sponsors, which is KLA and the 2 research groups, which is NCIS, Networks, Communication Information Systems, and Signal Processing, Image Processing, and Machine Learning. Anyway, the floor is to Johan. Please go
ahead. Thank you, Vijay, for that very nice introduction and for this invitation. It's a shame. I enjoy visiting Ann Arbor, and so I'm sorry to not be there. I was trying to think of the right joke to say about sort of how usually you come from something like the Bay Area to Ann Arbor and there's some weather joke that's sort of inevitable, that it's sort of colder or something like that. But you all definitely have the better weather this fall because we're kind of in constant fire season since about August. So the background photo that I've been using the last month is sort of, it's taken in with a romantic intent that it's some sunset over campus. But it's much more, it has a different meaning right now when sort of everything is on fire. So outside my window, the sun is orange, and I think your sun is not, or sorry, it's usually orange, it's orange pink. I think you have better skies above you right now. So I'm gonna take over, do some screen sharing and start my talk.
So I'll monitor the chat to see if there are any questions, and I may interrupt once in a while, but that's
great. That's useful because in my experience, once sharing, I lose sight of the chat unless I do a lot of clicking. So, okay. Thank you again. So today I'm going to talk about. So this is a ECE seminar, and I'm going to talk about sort of a learning problem in a discrete space that I think it has a lot of interesting optimization problems embedded within it. There's also some fundamental kind of like learning problems that I'll get to at the end about sort of the complexity of, or sort of lower bounds on the complexity of testing some important questions in these funny discrete domains. In particular, there's this domain that's going to be the centerpiece of this talk, which is sort of how we think about overlapping discrete distributions. That is kind of the fundamental object of discrete choice. This is joint work with Alex Peysakhovich, who's a researcher at Facebook AI in New York, and then Stephen Ragain and Arjun Seshadri are former and current PhD students here at Stanford. So let's introduce the elephant in the room, which is sort of discrete choice as a problem. It's the study of choosing things from discrete sets. And so there's a long history of discrete choice that kind of dates back to the early psychometrics work in the 1920s, but the modern study of discrete choice arguably comes out of the it was made very popular by the movement in econometrics towards discrete choice models, led by people like McFadden and Mansky in the 70s, who were studying transportation problems. There's a very large discrete choice literature in transportation. Sort of how are you, what mode of transportation are you going to use to get from A to B? Mansky was studying school choice problems, or actually not school choice in the modern mechanism design sense, but school choice in the sense of which school are you going to attend, or why do people choose to go to college versus get a job. That is a problem with a choice set and a choice, and there's a reason to apply those types of methods. Now, these days, there's a much larger emphasis certainly in the machine learning community on choice problems that are sort of click problems and web problems. And by this, I mean, you have slates of alternatives and you're selecting one of them. So this comes up in the design of front pages of news websites. It comes up in recommender systems on things like Netflix. And then it also, ads, which is not my favorite application, but online ads and sponsored search ads is certainly a sort of a domain where you have slates of alternatives and you're clicking on one or none, but you're sort of making some sort of choice, and a predictive model of behavior in that setting is useful for, in that sense, sort of which ads to show and predicting the click-through rates. In a lot of these settings, it's important to consider the existence of like an outside option. So the idea that you don't click on something is the idea that you click on the no option, or sort of like you choose the no click option. But those are the problems that have motivated a lot of the attention that these problems have gotten from the machine learning community over the last few years. So we're going to take a probabilistic approach to discrete choice, and we're going to think about the fundamental object as sort of a collection of distributions over all the subsets of a universe. So there's universe X, and there's all the sets that are subsets of that universe. And the agenda for today's talk is we're going to talk about, first I'm going to set up this idea of a choice system as a mathematical object. It's not every day you get to meet, if you've seen this before, hello, welcome. If you haven't, it's not every day you get to meet sort of a new mathematical object. Then I'm going to talk about this assumption that permeates a lot of work in choice, which is the independence of irrelevant alternatives. I'll introduce it, and mostly my intention is to step beyond it. So I'm going to introduce it and then talk about models. It's sort of an assumption that's sat at the center of discrete choice since at least the 1950s. And I'm going to talk about modern steps beyond assuming the independence of relevant alternatives. I aim to close describing work on how hard it is to test whether data obeys IIA. This turns out to be, there's been a lot of kind of negative results, or sort of like skepticism of how, vagaries about exactly how hard this testing problem is. And we brought some fancy modern high dimensional stats math to that question in recent work. So let's talk about the object of a choice system. So a choice system is this collection of all these probability distributions. And as a thing, it's quite similar to sort of, I think it deserves attention in the same way that people study the structure of, vector spaces like Rn, or, the surface of the sphere as a space. Out here on the right, we have, let me see if my iPad technology, of course my iPad froze, right? Okay, let's see here. The battery on my pen is dead. That can happen. Okay, so I'm going to charge that, and we'll have interactive, and have an interactive experience soon. So Sn off on the right is sort of the space of permutations. We have, tree space, you have the space of continuous functions, simplices, polynomial spaces. A lot of these are vector spaces. Choice systems are not. So what is a choice system? So let P of sub X sub C denote the probability of choosing X from C. So you should think of this as a probability distribution on the support, on a support that is the items in a set C. And that that's sort of the first sort of simple discrete distribution. But then we have lots of these discrete distributions, and we basically have one for every subset of a universe. So that's this definition that I have here that I'm writing as a conditional choice system. The word conditional will be explained in 30 seconds, but basically it's for every subset, you have the little histogram over the alternatives. Now, by using thing 1, I'm alluding to the existence of thing 2. So what is thing 2 here in my introduction? It's the idea of kind of an unconditional choice system, which is that separate from just thinking about these little distributions where you're sort of fixing the set and then asking about a discrete distribution over the alternatives. You can also think of a more general question, which is sort of, how do I know which set is being chosen from? And as a mathematical object, that ends up being sort of, okay, so I'm going to couple all these discrete distributions on sets with some distribution over sets. So far, so good. That in and of itself ends up defining an interesting high-dimensional discrete space. But we're sort of going to mostly focus on definition 1 first, where a lot of the learning focuses, but then the testing problem ends up centering itself around sort of the second definition, this thing 2. But the first definition is the one where somebody has kind of exogenously spotted you with what's on offer, and you're trying to predict what gets chosen. You're not trying to model the arrival process with which things are suggested. That's sort of exogenous to the process of just studying the conditional choices. Okay, so if my pen is working now, let's see if I have contact. I'm going to try and do a quick iPad restart. Of course, I quit the app and it didn't actually die. But I'm going to try and spend minimal time on this. Otherwise, I have backup plans. Yeah, so that's not working. So that's why we make backup plans. So I drew this in advance. So consider you have a set ABC, and I'm trying to give you a sense for what this object is. So consider all the subsets of ABC. There's the pairs and the triplet. There's 3 pairs and there's a triplet. And all I'm trying to tell you is that there's sort of a set of 3 histograms for the pairs, which is just the proportion of A to B, the proportion of B to C, the proportion of A to C. That's sort of what I'm going in the middle. And then there's a separate kind of 3-way histogram. Now, what I want to try and convey to you is that there is this, okay, I can use my finger, which is not a very good stylus, but you can think of those histograms as living on the following kind of object that I find to be useful, and I haven't seen described elsewhere in the literature, which is that you can think of the A-B choice as a point on the line segment between A and B, which is sort of the simplex of 2 alternatives. There's just kind of a line segment. You can think of BC as the choice between B and C as just sort of a proportion there. And you think of AC as a proportion on the other edge of this 3-way triangle. And then the 3-way choice ends up being this point on the sort of interior simplex. And the study of choice systems is really about the study of sort of the interactions of these facets of the simplex with the sort of higher order facet, higher order face. And it's about the interactions of sort of what's the relationship between pairwise choices and sets that contain those pairs? What's the relationship between 4-way choices and 3-way choices of subsets of that 4-way choice? So that's the kind of object that we're going to think about, and we're going to think about learning problems on that space where we're making assumptions about the relative structure of subset distributions and superset distributions. So the classic assumption that drives a lot of the modeling in this world is the independence of relevant alternatives. If you don't make any assumptions, you just for every subset, there's a discrete distribution. That's sometimes called an arbitrary choice system. McFadden calls it the universal logit in a way that we'll return later. But it sort of makes no assumption about the relationships between these different sets. And so what is the independence of irrelevant alternatives? I want to sort of do a little bit of a memory wipe. If you're thinking about it in a social choice setting from like arrows and possibility theorem, set that aside And we're just going to talk about the way that the independence of irrelevant alternatives gets used in discrete choice. So what it says is that for every pair of items x and y, the ratio with which you pick those items when they're a pair doesn't change when you introduce other things c into the choice set. So we have here this proportion of x to y, of the proportion of which x get chosen from xy to y getting chosen from xy. And that ratio will stay fixed when we add other things c to the choice set. So all the things in C there are irrelevant for the purposes of the choice probability of x and y. Putting those in there doesn't change the sort of relative power of x over y. And as a consequence, sort of the ratio between x and y stays the same no matter what you add to the choice set. And so models that obey IIA, and this is sort of a classic result dating back to Luce, they admit a ratio representation. So the probability of choosing x is proportional to some quality parameter, you can call it this like gamma, like the strength of x is sort of gamma x, and the strength of x relative everything else in the set. So the denominator there is really just a normalizer, and it's really about there's some like inherent strength of an item. I'm avoiding the word utility because I will come back to it. So what does IIA look like in this discrete space, in this funny space that I've illustrated? So if we have an arbitrary choice system, if we assume IIA, once we have sort of learned a little bit about the choice system, so we learn the proportion with which B is chosen from the set AB, and we're going to say that it's maybe a third, then that actually constrains what the triplet choice has to live on this sort of colored line. It can't be anywhere else because then it wouldn't be consistent with sort of adding an item to the set, not changing the proportion. Similarly, there's sort of a color coding here where once you've fixed that three-way proportion, you're also locking in the color of the two sort of subsimplices. So IA is a very strong assumption that closely couples all these discrete distributions. So this sounds like it's sort of a choice theoretic talk so far. So I'm going to now move into sort of learning problems and machine learning problems, or econometric problems, or statistics problems, whatever your favorite word is. I will not use AI as a word, though I do have an obligatory kind of robot on this slide. So assuming IIA ends up implying sort of is the fundamental assumption behind the use of the multinomial Logit model of discrete choice. So a lot of problems in discrete outcome spaces. So you're trying to predict, which animal an image gets classified as. A lot of machine learning problems in discrete outcome spaces that are more than binary fall into the category of sort of multinomial classification problems. And the multinomial logit is really just saying that we're going to consider predictions of choices from different sets. And that's sort of the workhorse of these types of problems of like, which of these ads is going to be clicked on, which of these movie recommendations is going to be clicked on, et cetera. And then also has its origins dating back to the transportation problems, the school choice problems, and sort of a long line of work in marketing, in mathematical sociology. There's been a lot of practitioners and theorists of these types of problems. And so to take an econometric view, we're going to, instead of just saying that there's this gamma, we're going to say that we're going to rewrite the gamma as sort of an exponentiated utility UX. And that parameterization connects the multinomial logit to random utility models, which we'll see in a slide. This idea that utilities are some random quantity, but that's sort of a forward pointer at this point. And standard applications say that the utility is somehow like a linear model in some feature vector. And the optimization problem, or sort of like the likelihood maximization problem, falls within the regime of sort of generalized linear models. There's this great hashtag that Daniela Witten coined on Twitter a month or two ago, which is IJALM. It's just a linear model. And it sort of is trying to throw shade on sort of people who are claiming that their models are really complicated. Actually, a lot of these models are just linear models. So if you haven't seen that, you can go look up that hashtag and enjoy some lively banter. So it's an assumption. Is it a good assumption? That's sort of a very important question. I mean, assumptions that are very strong can be very powerful when they're right because they reduce kind of the number of degrees of freedom, et cetera. But we're gonna, so here are kind of some waypoints in navigating like whether you think this is a good assumption. So the right off the bat, after Lewis completed his monograph in 1959, this is a bit of a history lesson, De Brugge, who's a prominent 20th century economist, is writing a book review of Lewis's book, monograph. And he says, oh yes, Professor Lewis's ideas are interesting, but here's why his assumption about the independence of relevant alternatives is a bad one. Because I've been sitting around and listening to recordings of Debussy and Beethoven, and sort of that's the choice set on the left. And I might be picking them in proportion to each other with some fraction, but if you were to ask me to pick from a choice set of 3 things where you added a different recording of Beethoven, I would not evenly distribute my probability mass. I would sort of unevenly distribute it. And the third Beethoven recording or option would steal unequally from the first Beethoven option and the Debussy option. So, but the book has merits, is sort of like the style of the book review. Like it's an interesting idea, but it's clearly a very strong assumption. That Beethoven Debussy example is like often referenced in this literature. Now, stepping away from thought experiments and getting into empirics. So there's work on search ads, which finds that ads can have a kind of a non-local lift on the click-through rate, sometimes called like a group effect. So you have a bundle of 3 ads, you add a 4th ad, and that ad lifts the overall click-through rate of all the other ads. And that is essentially means that it's taking from the outside option in a non-uniform way as it's being added. And violating regularity without going into details. So there's work on that, which is sort of, ads pays the bills. So there's been a lot of interest in that line of work. Finally, web browsing habits. This is a paper out of Google where they were looking at how people were navigating to choose restaurants. They found a lot of evidence for what's sometimes called a nested logit model, which is one way to violate IIA. And I'm not going to talk so much about nested logit models today, but they sort of find that, in the top diagram, you're first choosing between Italian and Japanese, and then choosing either traditional Japanese and sushi. And that leads to non-uniform sort of pushes and pulls in terms of how people are making choices. So, okay, so there's a lot of context where IIA is arguably not a good assumption. So let's talk now. Now I'm going to switch tack into talking about deviations from IIA now that I've kind of introduced this creature, this strong assumption in this space. So the first easiest way to step away from IIA is to take the classic regime of random utility models common in econometrics and change it a little bit. I'm going to briefly review that, but I'm not going to spend too much time on it because I want to talk about the other kind of what I would view as like the more exciting recent stuff that's happening, which is also where my work has been, which is talking about Markov chain models that can be used to get sort of either model choice under IIA or beyond IIA. And then this sort of perspective of a truncation of a choice system that dates back to Batzel and Polking, at least, that that I think is one of the more interesting directions to take the kind of the machine learning literature on discrete choice in. So all 3 of these perspectives, the Markov chain perspective, the random utility model perspective, and the truncation perspective, they nest IIA, they nest the multinomial logit as a special case, but they can step away from it in different ways. And that's what's kind of interesting. Note that I sideboarded the mixture model literature and the nested logit literature for today, which is a mistreatment of the literature for those of you who don't know it, and for those of you who do know it, forgive me. So we're going to derive different deviations of IIA from this perspective. So just to give you an idea, if you haven't seen this before, I feel like this at least I should tell you. So one way to get IIA or get to model discrete choice is to say that all the items have some utility plus noise. And the way that you're making choices is you're rolling all the dice. So there's 5 things in front of you. You let all those distributions realize, and then you pick the max. Right? So the first line there, I defined these random variables, and then I said that the choice probability was the probability of being the max. So in the little bumps in front of you, it's very likely that I would pick the pink option. Less likely I'd pick the blue, and the other options are really have very low choice probabilities. So it turns out, as a exercise in kind of probability, if the noise terms are independent zero mean Gumbel, then the probabilities end up being proportional to this mean parameter. And that you derive the MNL sort of. So another characterization of multinomial logit is to say that it's a random utility model with Gumbel noise. This is a fun exercise. It also sort of has, it's also an explanation. It's a random utility models are useful to understand in machine learning because of the way in which they underlie things like the Gumbel trick and other things in kind of other tricks that people use when dealing with with softmax or sort of like the logit functional form. So I thought I'd put it out there. I also, at this point, I just want to give a 1-bit flagging of the fact that random utility models can be quite weird. They're not as simple as you think they are. So for example, they need not even be stochastically transitive. To get there, you need to have kind of different non-identical distributions on your noise terms. But basically, if these different items have very different distributions, things can get really weird. The hook for those of you who want to understand more about that is to look up non-transitive dice. So non-transitive dice is this classic parlor trick of sort of discrete probability. And you can think of non-transitive dice as a random utility model that is not stochastically transitive. In recent work with a student, Ruel Makajani, we connect kind of transitivity to properties of the log likelihood. So it's particularly a log likelihood that is concave in an item level parameterization has to be transitive. So if there's an if and only if statement there. So if you want sort of a convex optimization problem, like the negative log likelihood to be convex, then you need to have in an item level parameterization, that's an important technical term, then you can only do transitive things. Non-transitivity in RUMs kind of, or in breaks when you have item level parameterizations. Okay, so stepping away a little bit, how far away from IIA can RUMs step? This is also a classic result, and you might ask why am I'm spending a lot of time on 50s and 70s results. I think that they're underappreciated given the recent attention on discrete choice post 2015. I think it's very worthwhile to spend time on these results that are well known in the discrete choice literature, but and the psychology, sort of math psychology literature, but less known in sort of the modern practitioner world. There are things that I've enjoyed learning about a lot. So there's this characterization theorem of what a RUM can do. So you might think how general is this idea of samples from independent random variables or not even possibly dependent random variables. So it turns out that a random utility model can realize a choice system if and only if, and here comes a jargon term, the Bloch-Marshak polynomials of the system are all non-negative. And so there's probably 2 people in the audience who know what a Bloch-Marshak polynomial is. They were polynomials coined by Bloch and Marshak in the 60s as an if condition. Falmain showed the only if condition. And this is what they look like. And I'm putting these down here because there's an iterative construction, and it's a mess. There's a huge number of them. But the first thing they assume is positivity. So they assume that all the probabilities are positive. Great, no problem. The next thing they say is that there's an if and only if for RUMs, that RUMs can only do things that are where the choice system satisfies regularity. So what does that mean? That means that for every choice set C, when you drop an item, Y, it can't increase the probability of any X. which basically means that or reverse, if you add items, nothing can get more, sorry, if you add items to the set, nothing can get more likely to be chosen. It's a quite reasonable assumption, and it turns out that RUMs can't violate it. So it's arguably not a controversial one. The higher order polynomials are less interpretable. As an aside, I don't know why people call these polynomials, because really they're linear constraints, but that's my opinion. But the real takeaway is that RUMs are not fully arbitrary. RUMs in the space of choice systems, they can only do some things. So here's an illustration of this. Again, this, I constrained the choice system by, I've spotted one value and said that, okay, the probability of B from AB is a third. I'm actually realizing that I illustrated this wrong, and that should be 2/3, because that's something that's closer to B than A. So I apologize for that. But so assume that this is the point 2/3. With IAA, the three-way choice probability lives on that line. If you're only assuming a RUM, you live in the following kind of polytope, rhombus, parallelogram. Whereas sort of IA, which is a stronger assumption, is in this the subspace of just that line. But basically, RUMs can do a lot of things. They can't do everything. Okay, so these are fairly classic results of sort of how RUMs can step outside of IA. Let's talk about more modern things. So the first perspective is Markov chains, where you can consider the following. You're choosing a digital camera, you're staring at them, there's 3 digital cameras in front of you. It turns out that you can define a continuous time Markov chain. The reason why it's continuous time and not discrete time is a longer story that I'll have to ask me about it. And basically, you can think of the stationary distribution on that set for some rate matrix or Q as a discrete probability distribution, sure. And then you can say, well, for every subset C, I'm going to restrict the rate matrix, and it's going to give me a distribution on that set. So there's sort of this single rate matrix Q that defines a collection of Markov chains, each of which gives you a discrete probability distribution. It's a way to define a choice system so far. I'm just telling you, it's like a way to define a bunch of interconnected probability distributions that have a single parameterization in terms of a matrix. Okay. So Meister and Gross-Glaser, go ahead.
The quick question is, IAA equivalent to reversibility, or?
Reversibility, good question. What IA is equivalent to is it's a particular parameterization where all of the rates only depend on the item you're jumping to. Okay. So basically all of the Qs are all about sort of like the take of that camera, and that is independent of where you're standing. So there's sort of an even more Markovian notion than just the pairwise notion. Okay. But so you can, yeah, so you can, I didn't go into this, but basically you can parameterize the Q in terms of like, not quite columns, but like omitting the diagonal, it's like the columns are constant. And so everywhere you're jumping is, or rows, I'm gonna get the transpose wrong. You're only jumping to things proportional to the quality. And then the stationary distribution ends up being the qualities on every subset, proportional to the qualities. So basically, so the reference to dig into for that question is this Meister and Gross-Glaser NeurIPS 2015 paper, where they show that if you do that, the parameterization I just described of Q, they give an iterative spectral algorithm for learning the MNL parameters. So it ends up being like Markov chainy and matrix solvy. And they show that the stationary points of the MNL likelihood is the same as the stationary distribution in the limit of a sequence of Markov chains. It's not just one Markov chain, it's a sequence. And this is where the continuous time Markov chain thing comes up. That hasn't been able to be escaped, though Shivani Agarwal and students at Penn had a paper that turned this into a matrix scaling problem, a single one, instead of a sequence of Markov chain solves. But there's been kind of this recent burst of algorithmic work that is sort of better than gradient, arguably not, but arguably better than gradient descent on the likelihood. So my own work in this area was a NURBS paper the following year, which more looks at this question of escaping IA and says, okay, that's a great way to learn M&L parameters, but there's a more general choice model here, which can do these pairwise things. And we kind of put various axiomatic labels on it. So we showed that these Markov chains don't need to satisfy regularity. So they can do things that RUMs can't, but they satisfy other things like something called uniform expansion that I won't go into. That said, in the more general class, likelihood maximization is a mess. You're taking like gradients over parameters of Markov chains, and it's not a good problem. But it works in practice. You can compute maxima, and you can study its properties on sort of small universes. If you're only looking at a total of a dozen alternatives, it's not a problematic method at all. If you're interested in these connections between discrete choice and Markov chains, probably an interesting starting point is this work by Negaban, Owen Shaw from 2012, but on rank centrality. This was what really kind of also opened the door that like Maestro and Grossglauser kind of built on, which is, so this is Devivraj Shah and Sewang O and the like. They observed that if you have comparison data and you do a random walk on comparison data, the stationary distribution looks an awful lot like the quality parameters of an M&L. And they got that's a lot like Maestro and Grossglauser's results, but they got it wrong. They made it really hard for themselves because they looked at the discrete time version. And with the sort of, if hindsight is 2020, the paper would have needed a lot fewer technical assumptions if they had set themselves up with a continuous time Markov chain. Now, there's other Markov chain models of choice that have been popping up in the literature. This Young Mishra Shafet paper was sort of contemporary. My own colleague now at MS&E, Jose Blanchett, has had a paper when he was at Columbia on Markov chain models of choice. The last is a paper that was sort of a recent machine learning paper that put this pairwise choice Markov chain inside of a neural net. And I was like, okay, sure, like kids these days, they'll put anything in a neural net. But there's sort of a bunch of people that are trying to use this way of stepping outside of Markov chains, or outside of IA with Markov chains in interesting ways. That was Markov chains. Let's talk about truncated choice systems. So wipe your mind, or please remember everything on Markov chains, but let's take a totally different perspective. So we're looking at choice systems and we're trying to model them in some parsimonious sort of like compressed way. And remember, let's start with the arbitrary way of thinking about things. So you have probabilities with which items are chosen from sets, and you're just gonna say that there's some like, in a given set, an item has a certain utility, and this is actually totally arbitrary. We're gonna put a constraint on it that they sum to 0. That's actually not that important. The more relevant thing is that there's sort of, an item has a utility in a set, and you switch the set, it has a different utility. So this is an arbitrary model. And this is what amounts to McFadden's universal logit model. The thing about this model is that you can take these like item set utilities and you can do an expansion where you say, well, let me consider a way to write out that probability. I'm gonna write it first in terms of some property of the item. Then I'm gonna say there are second order terms that are the ways in which items Y contribute in a push and pull manner to the utility of X. That's the second order terms. Then I'm gonna say that, well, okay, but there's also ways in which pairs of items push and pull on things. Sort of a tertiary, like next order, a third order interaction. And so on and so on. And it's sort of, this turns out to be kind of a unique expansion, sort of in the way that you would like do a Taylor expansion of a function of a choice system. And kind of Botswell and Polking worked this out in a paper from 1985, where they sort of also, they identified the constraints needed to make this unique, which is, the constraints are critical to kind of getting the degrees of freedom right. And this is fully Botswell and Polking's idea. They talk about the idea of a pth order model where you're kind of truncating the choice system in terms of only interactions out to the pth order. And they observe that there's M&L as the base case because it's just item level utilities. And on the other end of the spectrum, there's the universal logit. And in between, there's this interesting space of models that are a little bit outside IIA. So focusing on this first step outside IIA, if you do some manipulations, you can come around to the fact that the probability of choosing an item from a set in that model is basically this softmax, this sort of like logit of a bunch of push and pull terms, a bunch of ways in which items Z push and pull items X. So you can think of this as like a pairwise linear dependence of alternatives. You're not independent, but you're assuming that you're pairwise linear dependent. And the thing about this likelihood is that it's actually convex in these parameters U. So it's convex. Now, the natural thing when you're staring at a big matrix U that sort of feels like it's too large is to factorize it and assume that it's low rank. That is not necessarily convex, but the original problem is convex. And that's attractive because this model is actually quite powerful. And other than we know how to work with it, matrix factorization non-convexity, it's basically it's a convex optimization problem to learn these parameters. So I've focused on this sort of like idea of Batzel and Polking. There's a history to identifiability conditions that I'm not going to go into, but so Batzel and Polking, what they were actually doing is they did this clever thing in order to use least squares, because it was 1985, and they didn't have the last 35 years of optimization. So they didn't try to go for the MLE. They weren't thinking about like gradient descent on a convex likelihood. So they do this clever thing in log odds space, and they find least square solutions. But what we showed in this ICML paper was that actually the maximum likelihood problem is quite all right, and we can bound the expected error by a quantity that decays in the number of samples. And it's part of this literature that I think is just really beautiful, which is about kind of structure-dependent convergence rates. So in that bound, you see this quantity here, which is the lambda 2 of L. What is that? So that's a second smallest eigenvalue of a Laplacian-like object. So Nihar Shah down here in the reference has a version of this result for pairwise pairwise comparisons under MNL. That is what we generalize to get this result. And it's this really elegant observation that kind of what is lambda 2 of, in the case of pairwise comparisons, there's a very natural Laplacian that corresponds to a graph. And that Laplacian, if it's very easy to cut, then the convergence rate is slow. So what that means in this diagram on the right is that the thing that determines how well I can learn the parameters of this data, like, this camera was chosen over this camera, et cetera, is how cuttable this graph is to a certain extent. And so the things that you can do to learn faster is to have sort of an absence of cuts and to increase your samples. So increase your samples to counteract the cuts. So there's a whole interesting theory there. There are broader implications of this convergence rate. It actually applies to a recently introduced blade chest model, which is a pairwise. It actually applies to word-to-vec type models, because word-to-vec type models are doing the same softmax of pairwise interactions. That said, the people who actually do word-to-vec do it in special ways with negative sampling and other fancy tricks. So, and I'm not claiming that we have convergence results for what people actually do, but I have a convergence result for at least the objective they say they're trying to optimize. And then there was 2 papers at ICML this year, one by a Michigan team that are, I think, on this call on salient features, and then also a paper on sort of how do you do kind of behavioral engineering, like promoting a particular choice. In some ways, I'm not that excited about the empirical results. I find the object and like the convergence and the modeling to be more interesting. There isn't that great data for kind of validating these types of choice models and whether there are violations of IIA. And so when we wrote this paper on the context-dependent utility modeling, we had this transportation data, because transportation data is what discrete choice people have a long history of studying. And the y-axis here is log likelihood, and we find that our model, which is blue, we're on the bottom, we're doing better. The x-axis here is the rank of the matrix, or we're also benchmarking against mixture models. But in a lot of ways, I was sort of like not confident that there was actually IAA violations going on. And that's kind of what I'm going to spend I'm going to do a speed run of like a 5-minute run of this testing IAA problem, because it's actually kind of hard to know whether you're like overfitting to the data because you have more parameters, or there's like really an IAA violation going on. Because it's an embedding method, you get embeddings, they're pretty, you put them in your papers because they're pretty pictures. So let's talk briefly about testing IAA. So IAA, it's a strong assumption that gives you a lot of power when it's true. Is it true? So soon after McFadden and the original folks were studying, working with these logit models to do a lot of econometrics and discrete choice, they started developing tests for whether IAA was true. So the waypoint here, I'll start with this 1984 quote. This Hausman-McFadden test, which is one of the practical tests that you might have ever done if you've done this type of testing, is you do 2 sets of computationally convenient specification tests. But these early tests there's this criticism that's come up where it's like going to the 96 paper, majority of tests based upon partitioning the choice set appear to have very poor size properties. Huh. Okay, so like power is tricky. Going to the next one, tests of an IAA assumption based on estimation of a choice set are unsatisfactory for applied work. It's like, okay, so you're getting like bad false positives and bad false negatives. And then, modern work says like, oh, we're going to set up a battery of statistical tests that quantify IAA violations. And the tricky thing about this is that these tests tend to only catch certain types of violations. So in like the modern, like sort of like minimax risk of over tests type world, all the knowing tests have either blind spots or like there's this undefined sense to how hard it is to really test IAA. And that was the subject of this EC work. So why is IAA testing hard? It comes down to the classic joke of high dimensional statistics, which is the Anna Karenina principle, which is that all nulls are alike, deviations from the null all deviate in their own way. So what does that mean for IAA? It means that there's only a few ways to satisfy IAA, but there's many, many ways to be irrational. There's many ways to deviate from IAA. And here's sort of a citation pile. I'm happy to share these slides, but this is the recent work on finite sample lower bounds on testing that we're leveraging. There's a lot of heavy hitters in the modern stats literature in this citation pile. And so basically, the thing about IAA is it's this very weirdly divided subspace of all choice systems. It looked sort of linear in the way that I showed it to you, but actually because of the normalizations, it's a weird subspace. And so whenever you're doing these testing problems, you start by saying, okay, I want to ask, am I in the set or am I at least delta away from it? So that's the idea of defining a separation. That's this bullet. And so we do that on this weird sort of space. And then we say, okay, we want to, in order to say, is this testing problem hard? We construct a simpler test, which just looks at the uniform choice system versus a bunch of perturbations. So as a testing problem, that just means, is the data coming from uniform or is it coming from a bunch of perturbations that are more than delta away from IA? And borrowing from the Anna Karenina principle, if there's a lot of independent directions to walk in, where independent is an undefined term, you can think of it as orthogonal, but like roughly speaking independent, if there's a lot of directions to depart from IA in that are sufficiently orthogonal, then it's going to be really hard to tell if you're at one of the orange points or if you're at the green point. So there's a strict sense to which if the data doesn't contain choices from every subset, you don't know if IAA is satisfied on that subset. So in order to do a lower bound on how hard it is to test IAA, you have to somehow rely on like what sets are available. So taking an example here, if there's 4 items, we're going to say that the only sets that are available are the pairs and the quadlet. the following is, I'm worried that this is going to be a little bit of like too fast of a speed run, but I want to give somehow a gist of what's going on in terms of like I'd like to leave time for Florian to sort of give a commentary as he's generously offered to do. But essentially what you do is you say, the reason why this is hard is that we want to quantify the extent to which there are many deviations from IEA. So what you do is you construct the following bipartite graph. And that has the 4 items and all the sets that they're in, and an edge if an item is in a set. And what we want to say is that, we want to say that there are many perturbations from IIA. And so how do you construct many perturbations that are kind of independent? So here's the beautiful thing about this work for me. It's that it turns out that the right way to think about independent perturbations is that you have to satisfy a certain set of constraints. You want to have something that still projects back to the uniform. It's outside IIA, but it projects back to the uniform. So it turns out that there's a lot of different ways to do that. But in order to project back to the uniform, you need to sort of have the same, there's like a row sum and column sum notion that you need to, sets need to maintain their frequency and items need to maintain their choice frequency. So what that means is that when you're staring, I'm sort of going to put the cursor over here. When you're staring at an item 3, it needs to kind of occur. You can increase its probability in one set, but then decrease its probability in another. That's like a constraint. And then in order to make that change, you need to sort of find a cycle in this bipartite graph of changes you can make. So you're going to increase 3, but then, okay, in that set, you have to decrease 4. So that means you're going to increase 4 somewhere else, which means that you're going to decrease 3 in that set. That's like the role of this cycle. And so it turns out that finding many perturbations is about finding cycle decompositions in bipartite graphs that have a lot of cycles. So we get a lower bound, which is to sort of highlight what's going on. I'm going to sort of, if all the subsets are there, if there's an exponential number of subsets, we get something that a lower bound on the risk that starts at 1/2. A test with a risk of 1/2 is a coin flip. And if we can't lower bound the risk, if the lower bound falls below 0, we have like our theorem says nothing. It says, okay, there could be a good test. But we're saying any test that actually tests all of this in an information theoretic sense, it has to satisfy this lower bound where the number of samples capital N has to sort of get beyond this 2 to the n in the denominator. And that's if you have all the subsets. If it's only pairs, your capital N has to get beyond this n squared. So we don't have any upper bounds and we don't give a test, but we're just sort of showing that this is a very hard testing problem in a rigorous way. So to summarize this journey, choice systems are these beautiful things. I hope I convinced you that they're like this object of with interconnections that's worthy of study, and sort of coming as an enthusiast for applied mathematics. And then I want to sort of hope that I've made you aware of these doorways beyond IIA, either based on Markov chains or based on these truncations that are, the Markov chain perspective is very recent. The truncation perspective goes back to this Batzel and Polking work from the 80s. And there's a University of Michigan story here, which is that 3 or 4 years ago, I was visiting the University of Michigan and I was talking to friends there and they said, oh, you've been doing work in choice. You have to meet Fred Feinberg. And I'm going to embarrass Fred now because he's on this call. And we met and I described the Markov chain work and he said, that sounds a lot like my favorite paper by Batzel and Polking 1985. And I said, I've never heard of it. And it turns out very few people have, but Fred certainly has. And I was at the time already doing this other work on truncations, and it turned out to be like exactly the same thing. So all credit to Batzel and Polking, and a huge amount of credit to Fred for helping make the connection. But so there's these two perspectives. So there's been recent work on sort of like, now that we can do maximum likelihood on these models, people are having a lot of fun with it, I think. I'm having fun with it, and it's fun to see other people having fun with it. the last bullet then is the testing IA. In terms of a messy problem, we've sort of replaced ambiguity with rigorous pessimism in bringing in sledgehammers from out in high dimensional statistics. Here's a sort of quick overview of the work that I've been doing that's kind of choicey. I've been having a lot of fun with it. I haven't talked about choice models of networks. That's a very fun problem. And then a few days ago, we got a paper accepted on sort of ranking models using some of these models at NERICS. That's up on my homepage. Thank you for your time. Yeah, just thank you for the invitation and thank you for your time.
Thanks a lot, Johan. So before any questions come up, I'm going to give Florian a time to present, and then we can step into more questions.
Okay. Well, thank you. That was a great talk. That was my first ever, engineering talk that I've been on. Let me just see if I can share my screen. I hope you can share my screen. I think I have like 4 more minutes. Yeah, I have like 4 more minutes. So yeah, I'm in the economics department. I just joined Michigan basically in August, and I got this invitation. I think it's really cool because I have no background whatsoever in discrete choice, even though I'm an econometrician and economist, and this is one of the things that people have done. All I want to give you, because I have no background, I read that paper and I was like, oh, I've seen these formulas at some point in my life, I think, but I have no idea what they mean. So what I'm going to do in like 3 minutes is I'll give you a background on the economics of discrete choice. And then I basically have, I have a few comments, but I don't know if I have enough time. I basically showed that there's like...
Please go ahead and present your stuff. There's enough time for that. Yeah.
Oh, okay. But I have to be on another call at like 5,
sure.
But I can probably go a little bit over. Okay. Anyways, so what we have here is a random utility model that we've already talked about, and from an economic perspective, you can essentially define this as utility that has a deterministic utility of choice of your item X, right, that you choose out of your universe. And then to make it random, you just add a random term, an idiosyncratic error term for the actual person choosing that item. Okay, so far so good. And then I'm basically deriving this equation now based on economics, based on the random utility idea. Okay, then the idea is, okay, I choose this item xj out of my universe if the utility I get from xj is higher than the utility I get from anything else, which is my probability of choosing this, which is the probability. You can rewrite these terms is the probability that the difference of the idiosyncratic shocks is less than or equal to the opposite difference of the utilities. This is just rewriting the difference of 2 general random utility functions. Okay, so this is when I choose item j over everything else. Very easy so far. And then, and this is the critical trick, then you introduce something parametric. So just for my background, I do a lot of non-parametric stuff. So I really try to not make parametric assumptions on models, but sometimes it's just inevitable. And also the McFadden stuff is from 1980. So back then they needed to use a lot of parametric assumptions for computational purposes and so on. So what you do is you define a joint distribution on all of these idiosyncratic error terms jointly, okay? Jointly, and this is the key word here. And then based on this joint distribution, using this probability of choosing idea, you can just rewrite this as a standard integral equation, if you will, where f sub j is just the partial derivative of your CDF with respect to the j's position, because we're looking at the j's item. Okay, so far so good. And now you just have to figure out what type of distribution you place on your random terms. Okay, so you need to choose a quote unquote good model. And what a good model is has many different interpretation. So as we already said, Marshak, Luce, and then obviously McFadden, who I think even won the Nobel Prize in economics for what it's worth. he won that for these models, as far as I know, and analyzing them in depth. And they basically show that if you choose a Gumbel distribution, which is a extreme value distribution, and we had this example before, it's like the distribution of the largest rank of some IID random variables. If you choose this extreme value distribution for the joint distribution of the idiosyncratic error terms in your utility, then you can show pretty easily by computing this integral, you can actually derive that this probability takes the classical logit form. Okay, and we've already heard about what like classical logit, what the problems are with this, and the IIA assumption in particular. Okay, but from an economic perspective, if you think IIA is not satisfied, what's the next best thing to do? Well, the next best thing is you actually try to go back to your original problem, right? To your original utility problem, and just try to come up with a better distribution, okay? The problem is, and that is the problem that like people in the 1950s, 60s, and maybe 80s had before all of this optimization stuff came in. If you have a joint distribution and you need to compute this integral, this multivariate integral, or over a joint distribution, that's very, very complicated to do in 1960 and 1970, and sometimes even 1980s. And that's why this extreme value distribution is more of a, you know, a pragmatic choice, because you have IID extreme value and then you can easily compute this. McFadden himself, I think, even McFadden and later Kenneth Train, who is also a giant in economics of discrete choice, said that using a probit model, meaning that using the joint normal distribution or a joint normal distribution instead of IID extreme values, might give you models that don't run into this IIA problem. And obviously they don't. You can actually prove this, that it's very easy, and it should be intuitive because you're working with a joint distribution instead of just you know, independent IID elements. And probit wasn't really used so much because it was computationally super, it's very, very hard. If you have a lot of choices, you have a very, very high dimensional integral you need to solve. I think recently this has gotten much, much better and you know, more interesting and easier to solve, so that probit could be a way to model discrete choice without even having to worry about this IIA assumption. Okay, so this is just coming from an economics perspective and coming from an econometrician who does no work in this area actually, and just tries to understand a little what's going on. So that's the very basic, and that just adds to the very nice talk we've just seen. And then here is something again from an economics perspective, where I'm wondering a little, you know, how this new approximation idea that was introduced actually has an interpretation as a utility. Okay, so we have seen before that we can write this this like logit model. We can split it up into, okay, that's the distribution that the good itself has, or that's the utility that you get from the good itself, and then you have the utility of all pairwise choices, of all triple choices, and so on and so forth. And the paper that I'm discussing basically said that you should just truncate this model at the second stage. So looking at only the single utilities and the pairwise utilities, and then you have this this like factor structure. And then, you know, being an economist, I was like, okay, so this is the outcome, and if you reverse engineer it, what should be the utility that actually gives you this type of choice probability? And you know, I did this last night, so there might be some computational errors in there. I hope not. But the utility actually that should generate this, if you look at a random utility model, takes obviously this very, very simple form, right? You have your randomness here comes from your idiosyncratic shock, and then your actual utility function is not the utility of choosing a good, but it's essentially the utility of choosing, or of how other goods just affect your goods. And we had talked, or we have heard this in this talk, and it makes mathematical sense. But from an economics perspective, you know, if you're someone who chooses an item, you choose the item because you think it has, you know, more value to you than choosing something else. Whereas this you know, second order utility function here has you judge an item based on how it interacts with the other items, essentially. And this can have a lot of this can work in many cases, but from a very individual perspective, I would argue that in many choice settings, this can be a very strong assumption. Okay, and in the same vein, you know, the agent chooses the item if your idiosyncratic shocks are less than this not so easy to interpret, you know, functional form. One last thing, and that's basically just advertising some, you know, recent advances in econometrics in discrete choice. Again, I don't work in this. There's many ways in which people have gone and into many different directions away from the IIA assumption, especially because it is not always satisfied. One is the probit model, as I already argued. That's another parametric way of doing this. Then there's quote unquote non-parametric approaches where you try to not make a fully parametric assumption on F, but instead of making, so there's no free lunch, right? So instead of making a fully parametric assumption on F, you need to have a much stronger model, or a much more explicit model on how your utility is generated. And this is where a lot of econometricians have worked in, and most of these old models just work in a very low dimensional setting, so where you don't have a lot of choices. There's a lot to be done, in my opinion. Again, I'm outside of this field, but it really looks like there's a lot to be done in a more non-parametric way. And one way to overcome this is to use dynamic discrete choice models, where you actually say, okay, you have someone who needs to choose an item in repeated settings, which makes a lot of sense, right? If you go on Netflix, you have repeated choices. You know, every night you have another choice of watching another movie. But this additional structure where gives you a lot more data to actually deal with, and this additional amount of data allows you to identify many more things without needing to make a lot of parametric assumptions. And dynamic discrete choice models have been a very active area of research in econometrics. Not quite in the most high dimensional setting, but people are currently moving there. And this is all I wanted to say, and I've gone way over time.
Okay, thank you very much. So Johan, do you have any comments or anything to add to what Florian mentioned?
No, Florian, I really appreciate it. These types of discussant exercises are not the norm in my field, so you know, I really appreciate it. I can only yes and what you've said. So so a lot of the random utility work, you know, the work on probits, I do think it is one of these examples where it was hampered by computational considerations 20, 30 years ago, and now there's interesting things going on. There is a little bit of non-parametric random utility modeling that's been going on. I have some pointers like in my email, but like I agree that it's underexplored. It's another interesting direction. The one thing that I would sort of more concretely respond to was the idea about like trying to interpret the way in which the utilities are about these interactions.
Yes.
So you're right that it's like it's not tractable. So one way, or it's not particularly intuitive. But one way that you can try and I try and intuit about it is that you can think of there as being a item level utility still, that there is something like and you can even add features there. You can have like features in a linear model, features of items. You know, you can have the resolution of a digital camera and the weight and the price. And then you add these like push and pull terms. And maybe you even like start doing things where you put like a sparsity assumption or a prior, so that you're like, oh, like only certain things push and pull. And so we started thinking about that. I haven't published on that, but there's a like more marketing-y choice problem, which is like this data set of like, you're picking snacks from a set. And so the question, and conveniently like, oh, confirm some idea. So if you have a bunch of like snack food and then you put like a slim fast, like a diet bar in the set, it has like it has push and pull on like, it pulls from the snack, from like the chocolate bar and gives to the apple. Even though you don't pick it, you pick the apple over the chocolate bar. And so in that, there you can say that there's like, well, I'm going to put a prior and say that only some of these push and pulls are non-zero because I don't really believe that they're a dominant factor in the behavior. And so that's one direction that's squarely in line with your feedback that it's like not super tangible. But yeah, no, I appreciate the discussion.
So I had just a sort of a different sort of question. I mean, so you had this Venn diagram with three different sort of ways to think about these discrete choice models. Is there, so I guess computationally, which is easier, which is better in prediction? And I mean, in terms of how would you differentiate those three in some sense? Yeah,
some of them I can give you theorems, others I can give you intuitions. But so for the random utility models, if it's loaded and probed, it's well studied. But if you get into like how, I don't know, so there's the Bloch-Marchand characterization theorem, like polynomials, but I don't know if you have like an arbitrary CDF in the language or how Florian was presenting it. I don't know if there's like, sample complexity type ideas that have been really explored for like arbitrary distributions there. But for logit and probit, there's like those things. I guess there's two different questions. One is optimization, one is sample complexity. For the truncation, that's sort of the main meat of what we were doing with like these. So we have the expected, the bound on the convergence bound on the maximum likelihood estimate in expectation. In recent work, we also have a tail bound, so we can sort of like fully understand the error there. Their convergence is well understood. There's a related line of work on even like Plackett-Luce models, which are the ranking models, and understanding the convergence, the structure dependent convergence rates there. These ideas of like lambda 2s. And so, and that's mostly for things that sit very close to MNL. And then the present project of this talk is about expanding that and understanding how much further can you go. So an interesting question that's more computational is like, what happens if I allow for third order interactions? And I think that that's an interesting example where like, okay, well, then it goes from a matrix factorization to tensor factorization problem, if you're going to factorize it. Either you have like, you can maybe live with like going from quadratic to cubic number of parameters, but if you don't want to do that, you're sitting on a tensor factorization problem, and then you're importing all the computational complexity of tensor factorization, or in the worst case. So that's like there's certain things known there. Really, instead of just being this Venn diagram, it's really like a set of overlapping leaves of larger and larger sets. On the Markov chain side, it's a mess, and I have neither like a characterization theorem or like any like learning thing. I actually like stepped away from, I got so much more excited about the context dependent utility models because of like, because convergence guarantees, because I sort of know what I'm getting as opposed to with taking weird gradients of Markov chains. Yeah, there's more open questions than there are answers.
Okay, no, thank you. Are there any other questions in the audience? I know we're getting towards the end of the, little past the time. But.
I would ask one if there's time.
Sure, please, yeah.
Johan was being nice by saying I introduced this to him. I sent him the paper and then he wrote another paper on it. It's more how it went, but anyway. When we apply this stuff in marketing, and there's Nocha and Ellie are also here. We're all like quant marketing people. Like if we have Coke, it's not the same Coke every time. It's at a different price. It's promoted differently. It's located in different stores. So there's all these features. So you have to get the utility function right. And if there's any missing attributes, those are going to carry over into the epsilon and induce correlations. So it seems like a lack of IIA could be missing information in real world data. So it seems to me that a big open area is how to apply this when we have, like Florian said, these sequences of purchases in the real world, which helps us identify heterogeneity across people because you need that to do it. But also whether, like, I'm sure if Coke is available when Pepsi's available, those things are similar. They're really similar, so they draw from each other. And it almost doesn't matter what's changing in the environment, but it's probably not true for other stuff. So this seems like an awesome way, maybe generally, to suss out whether or not the core items themselves pull from each other, irrespective of all the other stuff going on. And I guess my real question for Johan is, we kind of distinguish the difference between having different error scales. So, you know, the typical model, the IA model, draws all of those error scales on the diagonal towards the same value, let's say 1, and it draws all the off diagonals to 0. So I'm kind of curious if your IIA tests can distinguish between the errors just having different scales or the errors actually having some correlations with one another. Because even the scale is going to break our IIA, like in the heteroscedastic extreme value model, the HEV.
Yeah, there was a lot going on there. Thank you, Fred. So I'm going to first just a comment about the sort of like the role of features, and I completely agree. So a lot of this, I've just been saying that there's like pushes and pulls of items sitting as in some latent space, basically. So conveniently, there's this paper. So one of the models that we nest is this paper out of the matchup literature for pairwise comparisons called the blade chest model, and that turns out to be about like, there's two vectors, one's a blade, you're pointing at my chest, it's like a fencing metaphor, sure. And there's a first paper that is just about latent space, and there's a second paper that's about matchups in context, and they merge the like latent features with features in hand. So it's about like you're making only pairwise choices, and really you can extend it into what we were, thank you, Florian, I saw your chat. You can extend you can kind of like basically add the explicit features to the latent learned features and explore the presence of these types of interaction effects beyond what's explained by basically like item level features by looking at that, like basically taking like the feature-based version, like from the blade chest model, moving it out to larger sets and taking it to a marketing data set that has good like feature vectors. I think there's a lot to be learned from an exploration like that. That's the first comment. The second comment was more, you were asking about sort of like testing IA and to what extent IA violations are explainable based on like missed covariates. Yeah, so that's a great question. I want to emphasize the fact that this like lower bound paper, it's like a lower bound paper and there's no actual test. Like we're not suggesting a test given data. Like we're just saying, we're looking at the fact that like the Hausman-McFadden test, it has blind spots in terms of violations of IA that could happen. And so it's not like admissible in the sense that it's like type 2, I'm going to get the types wrong, error is like blind to certain violations that it can't see. But, you know, if there are violations in the, you know, there's a fence post, there's a perimeter around IA that it sets up, and if it's in that direction, you're catching it. And that's just, so that's where we were like, we want, like, how hard would it be to catch all violations of IA was the question we were asking. And it's, the investigation is not really, it's very agnostic to like what the error is coming from. It's like, for example, you know, the other one where there's violations of IA in data is that actually the population is a mixture model. So whether it's like that or whether it's, there's some, like if you gave, so I guess to make your question most concrete in my language is like, if it was a feature-based model and the model was correctly specified, if it was like a linear model and the model was correctly specified, could you, how hard does the testing problem become? Or does the testing problem, does the lower bound go away? Like does the minimax, whatever, lower bound, is it no longer as pessimistic? And that's a good question that I will have to circle back to you about. Yeah, I think like you're still in trouble. Like certainly if you add like a intercept term, then you're starting to like be able to do arbitrary things. An item, or you add an item level fixed effect, you're back in as bad a news situation. But it might be that with a linear model with like a fixed set of parameters. Yeah, it's a good question. Thank you for it.
If there are no other questions, let's thank Johan for an excellent talk. I think that was great.
Thank you all for staying fast. Yeah.
He's around, I guess, online tomorrow as well. So if there are some slots to meet with him, if people want to meet with him.
Yeah, BJ set me up a schedule. So yes, please.
All right, thank you again. So I'm going to end the recording now. Thanks. Bye.
Yeah, thank you, BJ. Good to see you, Fred.